All right, class. Yeah, no one's in here. So I really don't get much out of this, but we're going to go through and do the notes. Same thing that we have been doing. These are going to be in your notebook on page 14 and 15. So the notes that you're writing down is going to be on page 15. You will have to just copy it down. You know, kind of like that thing where people used to do, the like write stuff down, paper, pencil, all that other stuff. But yes, page 14, 15 in our notebook. So this notes goes on page 15. And I did mention it, I will be checking notebooks this week to make sure that you have the notebook. You're starting to put stuff in it, and that you have it. So please have it this week. I will be looking for it. All right, so here's the notes. Oh, wrong page. There you go. So what we have is experimental and theoretical probability. Now, if you notice, we went from our previous set of notes, which is Unit 5, to Unit 7. Now, this actually flows a little bit better. It flows a little bit better. Yes, we skipped 6, but really not skipping it. We're going to come back to it after 7, because 6 is a short unit, and then this one's going to take us all the way up to spring break. So this is 7.1 notes on page 15. There we go. All right, now, so for these right here, students will distinguish between experimental and theoretical probability. So now, your vocabulary. So I have it nice and printed off here for you so you can see what the probability should be. Your vocabulary. Controlled operations that yields a set of results is an experiment. Your outcome is your possible results, and your event is sub-collection of outcomes of an experiment. And for your use, here it is right here, nice and big. And I am going to shorten these notes. I don't think it needs to be a really long video, because if you still need to copy it down, hit pause and then continue copying it. Alrighty. Let's see, there we go. Okay. Now, probability, the chance of something happening. So we have two different types here. We have experimental or empirical probability. Or it's empirical. So that's empirical probability or experimental probability of an event is an estimate based specifically on direct observation or experiences from a large number of trials. Next thing is theoretical probability of event is a mathematical of an event is a mathematical calculation of the number of ways an event can occur divided by the total number of outcomes. And probability, experimental or theoretical, is always a number It's always a number between 1 and 0 inclusive. Why does that look weird? There we go. All right. Now, 1 and 0. So it could include 0 and it could include 1. So it could be both or either. So expressed as a decimal, fraction, or percent. Now, here's empirical probability. In 100 tosses of a coin, 44 land heads up. Actually, let's go right here. So we have, for this one, got a formula for this. We have P of event is going to be number of times E occurred and total times number of experiments. All right. So for this one, for this probability, we have total is 100 tosses of a coin, 44 land heads up. So find empirical probability of the coin landing heads up. So it gives you heads up, so that means number of times is going to be 44 out of my total, which is 100. So there it is expressed as a fraction. Now if I divide that, that's going to give me a decimal. So this is my fraction. And then this is going to give me 0.44 as a decimal. And last one is going to give me a percent. And percent's pretty easy because it's out of 100%. It's 44%. That one should be pretty easy there. I don't know if I need to write the word percent, but I will anyway. So example, a pharmaceutical company is testing a drug that is supposed to help with weight reduction. The drug is given 500 individuals. The following outcomes. So 379 reduced weight, 62 unchanged, 59 increased weight. So if the drug was given to an individual, find experimental probability of the person weight is now reduced. So I go to that value that is referring to the reduced. So the reduced weight, so that's going to be referred to as P of reduced. And that's going to give me my 379 out of my total 500. And I'm going to divide that out. It's going to give me, let me see, that's 0.758. Or as a percentage, it's 75.8%. So you can go ahead and calculate this on your calculator if you need to. I'm just going through and plugging in mine for this. So the unchanged, which is going to be my 62, so P of unchanged, is going to give me my 62 out of 500, which is my 0.124, and that's going to give me about 12.4%. Now the increase is P of increase. Is going to give me 59 over 500, which is going to give me 0.118 and 8%. So if you have your calculators in front of you, you can calculate those, and they are rounded. And the next part, again, if I'm going too fast, go ahead, pause it. So the next part says, law of large numbers, probability statement applies to a large number of trials, not a single trial. The relative frequency over the long run is accurately predictable, not individual events or precise totals. Example, we all know the probability of flipping a coin and landing on tails is 1/2. Because there's only two sides to a coin, and you get one, tails is on one of those sides. Does it mean that if you toss a coin 10 times, it will land exactly on tails 5 times? No. It means that the number of tosses increases, the probability gets closer and closer to 1/2. So if you were to do it 1 billion times, it would be about 1/2. Because it's not always going to work out like that, but it does. Just over the long run, it will always come closer to that. So, I have a short little video for this. Hopefully it works. Dang it.
How does an insurance company decide how much to charge for car insurance? How do casinos set up payouts? How does an insurance company decide how much to charge for car insurance?
Dang it, why does this keep doing this to me?
How does an insurance company decide how much to charge for car insurance? How do casinos set up payout structures to make sure that they make a profit? How does a poker player decide whether or not to fold? How do we efficiently measure the appeal of a political candidate? The answers to these questions are informed by the law of large numbers. The law of large numbers states that as the number of trials or observations increases, the actual or observed probability approaches the theoretical or expected probability. This is important to understand because it allows us to predict and have confidence in how events will play out in the long run. Let's take a common example, flipping a coin. Assuming the coin is fair, we know that the theoretical probability of flipping heads is 0.5 or 50%. However, that doesn't guarantee that if we flip a coin 10 times, we'll get 5 heads. But we can be confident that as we continue flipping a coin indefinitely, the cumulative proportion of heads flipped should get closer and closer to 50%. Looking at this graphically helps to illustrate the concept. I just flipped a coin 20 times and these are the results. After each flip, we'll calculate the cumulative proportion of heads so far. So the first flip is tails. So our current proportion is 0 heads out of 1 flip, 0%. The second flip is also tails, so now it's 0 heads out of 2 flips, still 0% heads. Next flip is tails again, 0%. Then heads, now we have 1 heads out of 4 flips, 25% heads. Flip again and it's heads, 40%. Heads again, and we finally hit our theoretical probability of 50% for the first time. Let's keep going. This graph shows the observed probability approaching the theoretical probability. One common misconception, referred to as the gambler's fallacy, is that if the first 4 flips were tails, you're more likely to get heads on the next flip because the proportion is supposed to even out to 50% heads. This is not the case because each flip of a coin is an independent event. Its outcome is unaffected by all previous events. So if you start out with 4 tails in a row, it's not that you're more likely to get heads, it's just that in the grand scheme of things, 4 tails flips will get averaged with a huge number of flips that are expected to yield an even number of heads and tails, causing the proportion to approach 50% as the number of trials increases. Another version of the law of large numbers explains that the more people from a population that you sample, so the larger your sample size, assuming your sample is free from bias, the closer your sample average will be to the population average. Let's say you have a group of 100 people. Each has some number of dollars in their wallet. If we ask one person how much money she has in her wallet, we'll get our first observation, $49, which might be pretty far from the average of the group. After asking the second person, $29, and averaging that value with the first, we are likely to have a better estimate of the group average. As we continue this process of adding observations and thereby increasing our sample size, we'll generally get better and better estimates of the group's average. So the law of large numbers gives us a compass with which to navigate the randomness around us. Even though we can never predict the outcome of a single coin flip, we can know that over time about half of the flips will be heads. And in general, the principle supports the idea that a well-founded strategy that is followed consistently should win out over time, even though it might result in a few negative events along the way. Thanks for watching. See you next time.
All right. Okay. So hopefully that actually helped a little bit. So what we have here is, gotta get that one and change that over there. All right. So the law of large numbers. Okay, going with this example right here, 10 times. What is okay? Sorry. We all know the probability of flipping a coin half. Does it mean that if I toss it 10 times it will land? No. What it means is the number is tosses increase, the probability gets close of tails gets closer to 1/2. All right. E has likely outcomes, probability calculated, the weight formula. So my formula is P of whatever event will be number of outcomes favorable to E, whatever my event is, and divided by total number of possible outcomes. All right, so let's say, going back to the coin, okay, tails is one event, the favorable that we're looking for, and the possible outcomes is heads or tails, because there's only two sides there. And this example will actually make a little bit more sense when we go through these next things. So, a die is rolled. Find the theoretical probability of rolling the number 3. A die is a dice and has 6 sides. And we're not playing Dungeons and Dragons. We're not dealing with a weird 20-sided dice. But if you want to play Dungeons and Dragons, then yes, we'll talk about that later. But this one right here, so we have on a dice, there's only 1 3. So there is one number 3 out of 6 sides. So that's a probability. So 1/6, or as a decimal, you can go ahead and figure out the decimal by dividing that out. The next one, a 7. So if a 7, but you only have 6 sides, so that means that there is no 7s on one dice out of 6. There's no 7, so a 0 out of 6. So there's no chance of rolling a number 7 on that one. Next one, even numbers. So my even numbers are 2, 4, and 6. So I have 3 of those out of 6. And so that one will reduce to 1/2. So half of the numbers are even. A number greater than 2. Let's see, the numbers greater than 2 are going to be 3, 4, and 5, and 6. So 3, 4, 5, and 6. So that means there's 4 numbers greater than 2 out of 6. And that reduces down to 2/3. Now, a number less than 7. So on a dice, all numbers are less than 7. So that's going to be 6 out of 6, which reduces to 1. So that is a guaranteed probability there. All right, and that is it. Don't forget, like, share, and subscribe. Hit that notification button, and yeah, buy stuff from my merch store.